Ah,
Hey everyone, welcome back and let's write some more neat code today. So today let's solve design, add, and search words data structure. So this is another problem from the blind 75 LeetCode problems list. So this is the spreadsheet I've been using to track which videos we've uploaded for those 75 problems. You can see that most of the solutions have already been updated. And today we are working on this problem, a tree problem, add and search word. So basically another day, another problem from this LeetCode Blind 75 list. The link to this sheet will be in the description if you do want to take a look. So basically we're designing a data structure to efficiently solve this problem of basically adding words. We're taking new words, adding them to the data structure, and also we're being given words and we want to search to see if those words match any previously added words to our data structure. So we only need to support 3 functions for this data structure. One is just going to be the constructor that's going to initialize the object. One is going to be adding a word, and that one is pretty self-explanatory. So we're just given a string, a word, and then we're adding it to the data structure. Now this word could only consist of lowercase characters from lowercase a to lowercase z. And the third one is going to be the one where the bulk of the algorithm is going to be contained. So this is going to be the searching word. A answer is yes, because object one is searching a word and the word can contain any character from lowercase a to lowercase z, but there's one additional character it could contain, a dot character. And what we're told is that the dot character is actually like a wild card. It can basically match any character in the string. So for example, let's say in our word list so far, let's say we had just a string A, B, right? So this is what we have so far, and we're trying to search dot B. So basically, would this search match any words that contain so far in our data structure? The answer is yes, because the dot would match any first character, right? So this that we basically match this lowercase a, and then we do have an additional b, which matches the second character in the string. So a dot matches any character. That's what's going to be tricky for us to implement. Now, the brute force way to solve this problem is pretty simple, right? We would basically have a list of words and then just for every search, we would just say, okay, does this search match any of the words in the input list? Now, that's not going to be super efficient. A more efficient solution is going to require a trie data structure, aka a prefix tree. So this is what we're going to be using to solve this problem efficiently. I will say if you've never heard of this data structure or you've never implemented it before, you basically don't have a chance of solving this problem efficiently. But if you have heard of this data structure, it's pretty intuitive why this data structure is used in this problem. Basically, a prefix tree, right? So for example, if we were searching b dot dot, we would want to first find all words that start with the character b, and then check, are there any of them of length 2, because the remaining portion of this can match any string of length 2. So a trie is basically a tree that has some kind of root node, and each node can have up to 26 children in this example because we have lowercase characters from A to Z. So basically, each node is going to represent a single character, right? And then each node could have up to 26 additional children. And basically, a word in this case, for example, hey everyone, welcome back. Designate require DC into and so a trie is basically a tree that has some kind of root node, and each node can have up to 26 children in this example because we have lowercase characters from A to Z. So basically,
need more power, more control? Then you need VPS hosting from Hostinger. Say goodbye to server limitations and access more. More storage, more memory, more bandwidth and speed. More for your money. Free real-time snapshot and free weekly automatic backups. More security, less DDoS. More intelligence, AI assistance, and customer support. Get more of everything you need, pay less than you'd expect, and get your server online in minutes. Go to hostinger.com and get more. Trusted by millions worldwide. Hostinger. 3.
Each node is going to represent a single character, right? And then each node could have up to 26 additional children. And basically a word in this case, for example, this is A. If I had a B here and then another C, this is going to be a single word, right? And so if we inserted the word, let's say we added the word ABC into our try, this is basically how it would look like. Now, one additional thing we have to say is for a particular node such as C, we have to say this is the end of the word, right? Because what we're trying to say is we did not add the word A, we did not add the word AB, we've only added the word ABC, so we have to designate that this is the last character. Now, if we added another word, for example, AB, what we're going to do, we're not just going to repeat that. We're not just going to say, okay, now there's going to be a lowercase a here, then there's going to be a lowercase b. Notice how we already have those characters available to us. We're going to reuse these characters. So instead, what we would do, adding this word, we would say, okay, let's add an A. So let's start at the root, add an A. We see there's already an A that exists. Then we'd say, okay, from here, let's add a B. We see that a B already exists. So once we get to the end of the word, right, that was the last character, then we would just say, okay, designate this as an additional end of the word. So now we have two words along this path. We have one word AB, we have another word ABC. Notice how all words starting with an A are going to be here, right? We could have other words, maybe a T or something, right? And other words as well, right? Basically, all words that start with A are going to be here. That's what makes this efficient. That's why this is called a prefix tree, because let's say we wanted all words starting with, let's say we were searching something like this, right? We're searching A, B, dot, dot, dot. So we want all words, for example, or even one word of length 5 that starts with A, B. Then we'd go, okay, let's find A, then find B right here. And then we'd go through all possible children that it has, right, in the tree. We would do a brute force depth first search, backtracking type approach, and then we'd get a word. We would try to find a word like this one. So with that being said, let's run through the example. You can see at the above, the first word that we're going to be adding is bad. So let's add a character for B. Let's add a child for this A. Let's add a child for it D. So now we have inserted the word bad. We do want to designate this as the end of a word, so I'll just mark it blue, but in our code, obviously we're going to do something different. Next, we're adding another word, dad. So we have to start along a different path because these two words have a different prefix. One starts with a B, one starts with a D. So let's additionally add A and additionally add D. Once again, designating this as the end of a word. We're going to add one last word before we start searching. This one's going to be mad, so we don't already have an M, so we do have to insert that, and then we have to insert A and then D. Of course, this is going to be the end of a word. So far we have 3 words. All of them end with a D, but they all 3 of them have different prefixes. That's why they're along different paths. Now let's get to the searching part, the interesting part. So we're going to search for a word, pad. Now, so what we're going to do is we're going to start at the beginning, right? Are there any words pad in this? So first we're going to try, are there any P's? We're going to look, is there a P? We don't see any, right? We only have B, D, and M, so we don't have any words starting with a P. That means immediately we know false. Pad does not exist in our input. That's why in the output over here, you can see false is what's returned. Next, we're searching another word. That word is going to be bad. So we're going to start at the root and see, are there any B's? We're going to see that, yes, we do have a B over here. The next character in the string is A, so does this B have a child A? Yes, it does. It has an A over here. the last character is a D. Does this A have a child D? Yes, it does. It's over here. Now, we found the characters we needed, but now lastly, we have to say, okay, the last character that in the searching word is D. Is this in our try? Is this designated as the end of a word? Since it's marked blue, it is. Therefore, we're going to return true for this input searching word. And you can see that's what's written in the output. This returns true. Let's go through the last two search examples. So in this example, we have .AD. So what does that mean? Remember, the dot character means we can match any character. So we're going to start at the root and we're going to go down all three paths or literally any of the paths. And to do that, we're going to have to use depth first search, or basically a backtracking approach, right? And remember, we're only looking for one word that matches this, right? So let's say the first path we decide to go down is this one, right? So this is a B, and we're allowed to use a B because the dot matches any character. So this matches so far, right? Next, we're at the next character, A. Does this path have a child A? Yes, it does. So we found another match. Next, we're looking for a D. Does this have a child D? Yes, it does, and it's designated as the end of a word. So in this case, we found one word that matches this, and that's all we need. We just need one word, so we are going to return true, and you can see that up above. Now, if this one did not match, for example, if this wasn't designated as the end of a word, or maybe this was instead an X character, we would say, okay, we didn't find a match down this path, but it doesn't matter because remember, the dot matches any character, so we don't have to go down this path. Let's try going down this path, right? And we would do the same thing. We'd say, okay, we have an A, we have a D, that means we found a match, that means we can return true. And you can see that this is not going to be super efficient, right? We would have to go through every single character that's in our try decision tree. But it's still more efficient than a brute force approach, especially for this last example. So we're doing one last search, and in this search we start with a B, but then we have two dot characters. And the reason this is more efficient with a try rather than just brute forcing every list, because this at least tells us, okay, we're starting with a B, so what we're going to do in our try decision trees, we're going to say, okay, every other word that starts with any other character than a B, we're not going to consider them. And we have a pretty small try right now, but it's possible we could have a really big one, right? So what this does for us is it eliminates a lot of the possibilities. We say, okay, at least we know we're starting with a B, and yes, we did find a matching B. So we can go down this path. Now we get to the brute force portion where we have a dot, right? So basically, in this case, it's simple because we only have one child, but maybe we'd have multiple, and then we'd have to go down all of those paths. But in this case, it's simple, right? Let's just check, do we have any characters that go below it? Yes, any character will match this first dot. Now we're looking for another second dot. Do we have any characters that match it? Yes, we have a D, and it's the end of a word, so yes, in this case, we also found a match, so we can return true, just like we have up above. So once you can kind of understand this visual example, it's not super hard. Now it's time to actually implement the code, and I'll admit that it's actually a little tricky, but I'll try to guide you through it. So one thing I like to do for try problems is just define a try node, because it's going to have a couple variables. So in the constructor, we're basically going to initialize two fields. So for this try node, we are going to have a list of children. Now I'm going to use a hash map for that. So basically what I'm going to say is for each character, we're going to say something like, A is mapped to a try node, and we could possibly do that for every lowercase character from A to Z. And for every character, we also need to designate if it's the end of a word. So I'm just going to use a Boolean for that, call it word, and initially we'll set it to false. And so basically the only thing we need to do for the constructor of the word dictionary is just define a root. So let's call it root, and it'll just be a try node. So initially you can see that we don't have any characters inserted, right? We just have an initial empty try node. It doesn't have any children, so no characters are inserted. Next, we are going to do the add word portion. This portion isn't too difficult, so what we're going to do is we'll set current equal to what our root is. So self.root is where we're going to start, and what we're going to do is basically go through every single character in the word. And what we're going to do is we're going to check if this character is not already inserted, because it's possible this character could already be inserted in the try. So we're going to check if C is not in current dot children, of the current node's children. If C is not in there, then we need to obviously insert it, right? So what we would do is say current.children of C is going to be a new trinode, where we inserted a trinode corresponding to the character C. And then, of course, what we're going to do is we're going to update our current pointer to this new trinode. If it didn't already exist, that means we just created it. If it did already exist, then we just shifted over to it, right? What we're ultimately trying to do is insert every character from this word into our trie. And once that's been completed, what we're going to do at the end is say, okay, current dot word is now going to be set to true. So we have created the characters and designated this as a word. Okay, now for the actual meat and potatoes of this problem. And this part is actually going to be recursive, and let me show you why before we actually start doing the recursive portion. If it didn't already exist, that means we just see. And then, of course, what we're going to do is we're going to update our current pointer to this new trinode. If it didn't already exist, that means we just created it. If it did already exist, then we just shifted over to it, right? What we're ultimately trying to do is insert every character from this word into our trie. And once that's been completed, already exists, then we just shifted over to it, right? What we're this new trinode. If it didn't already exist, that means we just created it. If it did already exist, then we just shifted over to it, right? What we're ultimately trying to do is insert every character from this word into our trie. And once that's been completed, what we're going to do at the end is say, okay, current dot word is now going to be set to true. So we have created the trie to the character C. And then, of course, what we're going to do is we're going to update our current pointer to this new trinode. If it didn't already exist, that means we just created it. If it did already exist, then we just shifted over to it, right? What we're ultimately trying to do is insert every character from this word into our trie. And once that's been completed, what we're going to do at the end is say, okay, current dot word is now going to be set to true. So we have created the characters and designated this as a word. Okay, now for the actual meat and potatoes of this problem. Hey everyone, in a moment. So for if it did already exist, then we just recursive, and let me show you why before we actually start doing the recursive portion. So this is going to start similar to what we had before, right? So current is going to be initially set to, let's say, self.root, right? And then what we would want to do is go through every single character in the word. In this case, I'm actually going to use the index of the word, and you'll see why in a moment. So for I in range, length of the word, and then we're going to get the character at position I, so word of I. And so remember, this character could be any character from A to Z, in which case the problem would be straightforward, right? We would just search our try and see, does this character already exist? And then we'd continue. If it doesn't already exist, then we would return false. But we know this character could actually be a dot character. That's what's going to make this tricky. So if C equals a dot character, the else condition is if it is a regular character. Now let's start with the else case because it's a little more simple. So if C is just a regular character, what are we going to do? We're going to check if C is not in current.children. That means this character does not exist. We needed this character to exist. We're searching for this word, but this character does not exist. So what do we do then? Well, simply we can just return false. That means we know for sure this word does not exist. If it does exist, then obviously we're going to shift our current pointer to that node. So we're going to go to current.children at character C. And then we would just continue our algorithm, right? But this case is going to be a little bit more tricky because remember, if the character is a dot, that means potentially we're going down 26 different paths because this dot could match any of the 26 characters. And we can't really do that iteratively very easily, right? We are going to use backtracking or recursion to help us do that. So for example, let's say we had a string like .ab. What we would want to do then is say, okay, dot, it could match any of the possible characters. So what we would say then is we would go through for every child in current.children values, because remember, for current.children, that's a hash map, and then we want only the values because those are going to be the actual children. So because we know the dot could match any character, so for this dot we would basically match every single character, and then we'd say, okay, for each of these we want to do the recursion on it, so we want to do the depth first search on this. And when we're actually doing that depth first search, it could just be an iterative matching. So what I'm trying to get at is that this entire thing that we just wrote is the recursive function. This is the depth first search, right? We have the iterative portion here where we don't have a dot, and we have the recursive portion over here where we do have a dot. So let's wrap this entire thing inside of a depth first search function. Depth first search, DFS, and so let's just tab it over. So now let's think about it. When we're doing our depth first search, what are we going to pass in? Well, we want to know what's the remaining portion of the word that we are trying to match, right? So we would want to pass in the index. So let's call that J. We're passing in the starting index J, right? And the other thing we're passing is what's the current root or the current node in our try that we're at. So in this case, if So depending on which one of these we're iterating through, we're going to pass in that child node, right? So that's what the node that we're going to be passing in, whatever child that is. So that's how we're going to call DFS. So let's define that up above. So J is going to be the index parameter, and let's call root what the node that we're passing in is. So, okay, so current is, instead of being called self.root, it's actually going to be initialized to the root that we end up passing in. And okay, so here I passed in J, but what we would actually pass in is going to be I. Actually, not just I, but I plus 1, because we're going down a child. So we're going to pass in I plus 1 as the index of the character that we're looking for, right? Because what we're saying is we're skipping the dot, so we're going to have to increment I plus 1. And this function is going to return a Boolean. So if this function ends up returning true, that means we found one path that matches. And remember, if we find a path that matches, we return true immediately. We're done. We don't have to do anything else. If we don't find a path, we're going to keep going down all possible paths until we do. If we never find a true, if we never find a match, then we're going to return false. Oh, and one more thing. So initially up above, we said I is going to go through range of the length of the word, but we know we could be starting at a different position. Here, we're always going to start at 0. We don't want to do that. We always want to start at J, whatever it happens to be. So that is the main recursive portion. And the last thing is, let's say we were given a word ABC, and the last thing is, let's say we were given that we always want to start at J, whatever it happens to be. So that is the main recursive portion. And the last thing is, let's say we were given a word ABC, and let's say we found a match, right? We didn't have any dots in here. What would that do? Well, we'd go through the for loop, we'd always execute the else condition, and we would always find the current node, and then the entire loop would be finished. Then what would we want to return out here? Well, we would want to return whatever current happens to be. So if current.word is true, then we would return true. If current.word was false, then we would return false. So we can just leave this as it is. So that's the main portion of this algorithm, to leave this true. If current.word was false, then we would return false. So we can just leave this as it is. So that's the main portion of this algorithm. The last thing that we want to do is actually call this depth first search function, right? So what are the parameters that we're going to give it? Well, we're always going to start at index 0, because we're going to start at the beginning of the word, so we can pass in 0 for J. And we're always going to start at the root node of our try, so we can pass in self.root as the root node, and then we would just want to return the result that this DFS function returns. So as you can see, this function right? So values, because remember for current.children, that's a hash. We return true immediately. We're done. We don't have to do anything. Go through the for loop. We'd always execute the else condition, and we would always find the current node, and then the entire loop would be finished. Then what would we want to return out here? Well, we would want to return whatever current happens to be. So if current.word is true, then we would return true. If current.word was false, then we would return false. So we can just leave this as it is. So that's the main portion of this algorithm. The last thing that we want to do is actually call this depth first search function, right? So what are the parameters that we're going to give it? Well, we're always going to start at index 0 because we're going to start at the beginning of the word, so we can pass in 0 for j. And we're always going to start at the root node of our try, so we can pass in self.root as the root node, and then we would just want to return the result that this DFS function returns. So as you can see, this function did work, and it does work pretty efficiently. So if you didn't already know what a try was, I hope that you learned that today. So this